More of a problem, kind of a sort of a physics problem we can do with this is hydraulic problems. So we'll probably give you one of these on the homework. I did get the homework started for those of you who are bored studying for the exam. I think I've only got 4 or 5 up there. And I put the due date next Thursday because I'll almost certainly be behind and because of the exam. So next Thursday is homework 10. Okay, so hydraulics. All right, there's just another example that we can do is basically fluid flow for mechanical control. So hydraulics lets you apply a large force or lets you apply a lot of work to something without having to apply a huge force. The one that you experience the most is your car, right? So most of you probably still drive these days, or does Lyft take everybody everywhere? All you, how many drive? Everybody drives, right? We all drive. Has anybody been driving when the hydraulics of their steering went out? Yeah. Was it hard to steer? Yeah. You're like, oh my God! Hopefully you weren't going very fast, okay? But if your hydraulics or your steering go out, you will realize it actually takes a lot of force to turn an automobile. You have to actually kind of lean on the wheel. I don't know if that can happen anymore. I don't know if they even use hydraulics. I hope, yeah, they must. I don't know. Hopefully they have a better way coming soon, because when the hydraulics go out, it's not pretty. Let's see. So let's draw something hydraulic, and let's keep it car related, because I'm just like a total gearhead, like that. Let's keep the car stuff going here. So what we do in hydraulics is we put a platform on the liquid. So at first we just have the liquid here. La la la. So we're kind of at a hydrostatic problem again. Liquid. And we put a platform on here like this, a little solid object. Put a platform on here like that. So put platform on the liquid. Okay, that's going to make it somewhat useful. The liquid has some density rho, right? We've been using that a lot. And then we want to say how much force to do this. How much force to hold up a car, right? So we're going to draw it like this again. Let's see, this time it's going to look like this. And on this platform, we're going to sit, right? Remember, there's actually liquid under there. There's no actual air in between. We're going to sit a car. When you draw a car, always draw the wheels first, because if you do, it comes out totally kick-ass like that. See, look at that. Always draw the wheels first. And the car weighs 1,500 kilograms, right? And we're going to see if we can use hydraulics to push down and lift the car. Okay, so we're going to have something, our finger holding it down here to where the difference in height is, let's see, I don't know if I gave a number. 1,500 kilograms. Where's the height? 10 centimeters. All right, can we lift the car? I didn't draw this as 10 centimeters clearly, but can we lift the car 10 millimeters? Rho, G, H. Oh my God. See, I did this so detailed. Oh no, 10 centimeters. Sorry. Okay. That's the question is, what would it take to make that happen? What force would we have to push to make that happen? Again, we have density rho. Let's see. Yeah, rho equals sort of like an oil is sort of 700 kilogram per meters cubed. It's kind of low, but that's the number I used. Okay. So look at that and say, I was thinking this had to do with the continuity equation. I don't know. And say, we got to use a lot of our laws to do this, right? So one law is our static stuff. Remember, we can get the depth, the pressure at the depth in some column. But we can also have that rule that says if I draw a dotted line across a continuous liquid, here, then the pressure is the same all the way across the dotted line. Right, we got to use that. Yeah, okay. So we're going to use that and say then the force on this area is equal to, the pressure we get here is equal to the pressure we get here. Right? Because it's static, it's a continuous fluid, it's the same fluid, it's not moving. So let's look at this little plate here, And I forgot, I need the areas of these things. So this is a 4 by 2 meter platform. Just giving you some realistic numbers here. And this is a 10 centimeter by 10 centimeter platform. All right, there we go. So we'll start setting this up and see what happens, okay? Okay, first, what is the pressure here? Okay, so this is where we're going to think. The fluid is doing nothing, right? The pressure there, well, it's like at no depth. So on the left, let's say the pressure is P atmosphere plus however hard we're pushing down. So in terms of strategies for solving problems, what I want you to realize is when we put something on a fluid and push, that's sort of part of the P naught. Remember? So P naught is this thing. So when it was just a fluid exposed to air, we called it P atmospheric pressure. When we sit something on there or we push, you just add that to the atmospheric pressure. Okay? So FP over 0.01 meters squared. Right? The force per unit area. 0.1 times 0.1 is 0.01. See? We like to solve problems. Can you explain that diagram? What is a square in the middle? Oh, this isn't a square in the middle. I was just showing you that this is 10 centimeters. I was just telling you the height between the two. Right? That's H. I'm not sure what the number is. I'm trying to find it. We'll get to it in a minute. Okay? So on the left, so that's the pressure right here. Right? The weight of the fluid is doing nothing. That's just the pressure right there. Now let's go across. And then let's say it's the same as the pressure right here. Okay? So that has to equal right. It has to equal this side. Okay? Now what is the pressure right here? Oh, we go to this equation. It's the pressure at the top plus rho GH. What is that rectangular cutout? Yeah, I don't know. There's no rectangular cutout. Let's see. I don't know. I don't know what a cutout is. Okay. So the pressure on the right. Let's see if we can get it. The pressure here. Pressure at the top, P atmosphere, plus what does the car create? Its weight, 1,500 times 9.8, over its area, 8 meters squared, right? 4 times 2 is the platform. So those two together are rho naught. Rho naught. Or P naught, I'm sorry, not rho naught. All right. This is why we don't do problems. Okay, it's too hard to keep up with problems. Is H 0 on the left? Yeah, you could call it 0 if you want. Yeah, so we call this 0. Right, all that matters is the difference. Right? Oh yeah, so rho GH on the reason H is 0 on the left is we're not at any depth. Right? This is rho GH or rho GD, how deep you are in the fluid. What's our depth in the fluid? 0. So I didn't write that term. We're about to write it over here. Rho naught plus, here you go, 700, 9.8. That must be the part where I said how deep it was. Yeah, 10 centimeters. Everything was 10 centimeters. Times 0.1. Right? 700 times 9.8 times 0.1. There's all the numbers. Right? All those numbers, you could plug in and see what it takes. Oh my God, a picture that's highlighted. I'm not on Snapchat. What the hell is this? You drew on it? I don't know how that works. Platform. What is this? This is just air here. I'm standing there. Okay, that's not anything. This is like a continuous fluid. Here's like a fish living, bubbles, the fluids here, and this is, yeah, there we go. There you go. Okay, so the area of this thing is 10 by 10 centimeters. We lifted it only 10 centimeters. And then you can see all these numbers we knew, except FP and the atmospheric pressure. We know that, but it's the same on both sides, right? The atmospheric pressure isn't going to make a difference. So now we're just down to the pressure we push here has to equal the pressure at the depth of that fluid there. Then why is the car higher than the person? Sorry, I'm lost. Because I pushed down. See, FP, we push down, we hold the car up. Right? If you just let it sit here and these roughly weigh the same, then these don't weigh anything. And we're pushed down this, we lifted this up. So we're just asking, how hard do we have to push to hold this up in the air? That's all we're asking. Right? Let's get the answer, and then I'll tell you why it's interesting. We have the answer. FP over 0.01 squared. This is all numbers, right? This is all numbers. So you could do the algebra, and you get 25 newtons. Oh, my God. FP. We just lifted a car by pushing with 25 newtons. That's only 2.5 kilograms of weight. That's not much. I could hold 2.5 kilograms, okay? So we lifted a 1,500 kilogram car with the equivalent weight of 2.5 kilograms. So the way we did that is because fluid distributes the pressure. So whatever little pressure we apply here in this little area gets distributed over this huge area. And it lifts a car. That's how hydraulics works, okay? We can't gain energy doing this. We'll do next what happens, how much work you have to do. But that's why you can turn your wheel when you drive and turn your whole car. Didn't it ever bother you when you're driving that I just turn this wheel and the whole car goes that way? Like with one hand while you're looking at your phone? Didn't bother anyone? Oh. Yeah, it's a physical intuition problem there. It's all from driving. Let's see. Okay, so that's the amazing thing there. You're so blown away, you're speechless. But now we didn't use continuity, did we? I could have done that last week. We just ran out of time. We haven't used continuity for anything. We did that whole problem with just static fluids, because it is a static fluid, right? Let's see. Yeah, that's the old message. Okay. Okay, so now apply continuity to lift the car 1 millimeter, push down. How far do you think you're going to have to push down? 1 millimeter? No. That's because you don't think about what's happening when you're driving. Did you just say the fluid distributed the area? I said it distributed the pressure. Right? You applied a pressure here to the fluid. That same pressure was applied all over the place, and it was also applied here. Not the exact same pressure, because the weight of the fluid pulled it down a little bit. But this pressure was applied over this whole area, and then a somewhat smaller value was applied over that area. All right? Okay. Let's see. Okay, so now we're just going to use continuity to see why this... damn it. Okay. Okay, we're going to use continuity to say what if we push down the delta V over here, right on this side. Say we push down is what? We push down, the area was 0.1 centimeters, I'm sorry, 0.1 meters times 0.1 meters. That was the area times how far down we pushed. Call it D. And whatever we displaced here has to be what pushed up there, right? So that must be 4 meters by 2 meters, right? Because that's this area. And how much did we say? 1 millimeter. What would it take to push it up? To lift the car 1 millimeter, 10 to the minus 3 meters, right? Area times delta x, area times delta x. We're just saying those have to be equal. See? And the answer is something really big, 0.8 meters. So if you had this weird lift for a car, you could push with 25 newtons and lift a car, but you'd have to push almost a meter for it to go that much, right? The car wouldn't move much. And that's how we avoid creating energy, right? If you calculated the work you had to do to lift the car, it would come out the same. The work you do pushing this down equals the work it takes to lift the car that high. It's just a way of getting to do it with less force, right? It's a mechanical advantage if you're going to be an engineer. There you go. So that's just the first example of the continuity equation. All we're saying is the volume that flowed down here is the same volume that flowed up there, because area of volume equals volume. Area times delta x equals area times delta x. Okay, it gets weirder, but that's just a typical hydrophobic or hydraulic problem. So we're assuming the boards are only 2D. I don't know what that means. Okay. Let's see. Where is the delta x from the right of the equation? Delta x is this. I lifted it you can't see it because the board won't stay up. I lifted it 1 millimeter. So that's delta x. That's 1 millimeter, 10 to the minus 3. You got to get fast with your scientific notation. Okay. All right. Oh, my God. 0.8. I got 0.8 when I did it. I am capable of mistake, highly unlikely. Okay. Okay. So in